Today, we are exploring a health issue that affects communities around the world: arsenic contamination in rice. Rice is a staple food for over 3 billion people, but what many don't realize is that it can also contain elevated levels of toxic element, arsenic. This contamination doesn't just affect rice quality and yield, it also has serious implications for human health. To understand how arsenic enters the food system, we turn to the science of geochemistry. Arsenic reaches rice paddies from several sources. In many regions, it occurs naturally in the local geology, especially in rocks rich in sulfides or ancient coal seams. However, in heavily impacted areas like parts of the South and Southeast Asia, the main source is arsenic-contaminated groundwater used for irrigation. Historical use of arsenic-based pesticides also has left residues in agricultural soils. Rice is unique among cereal crops because it is typically grown under flooded conditions. These low oxygen environments change the soil's redox chemistry, converting arsenate into arsenite, which is more toxic and more easily taken up by rice roots. At the root level, an important geochemical feature is the iron plaque, a layer of iron oxides that forms on rice roots. This plaque can bind the arsenic and reduce uptake, but under certain conditions, it may actually facilitate arsenic transport into the plant. This interaction is complex and still an active area of research. Long-term exposure to inorganic arsenic through diet is associated with a range of health risks, including cancer, cardiovascular disease, and neurological effects, especially for children. The World Health Organization sets a limit of 10 micrograms per liter for arsenic in drinking water, yet this limit is often exceeded in groundwater used for agriculture. Fortunately, geochemical tools are helping us monitor and manage this problem. Techniques like ICP-MS allow scientists to detect arsenic in rice and soil at extremely low concentrations. When combined with HPLC, we can also distinguish between arsenic species, which is an essential step in assessing health risk. These geochemical tools have also guided the development of mitigation strategies. One promising strategy is to reduce arsenic uptake is the application biochar, a carbon-rich material derived from biomass. Biochar can bind arsenic in the soil, making it less available to rice roots. Modified forms of biochar enriched with iron and manganese can enhance this effect even further. Another important solution lies in water management. A method known as alternate wetting and drying involves periodically draining the fields. This changes the soil's redox state, stabilizes arsenate over arsenite, and can significantly reduce arsenic accumulation in rice grains. The movement of arsenic from soil to grain is driven by complex geochemical processes. By applying tools like ICP-MS, HPLC, and using materials like biochar, and implementing smarter irrigation practices, we can reduce exposure and protect the health of rice consuming communities worldwide.